The problem that we're posed with here is we have a gate which is meant to control the water level in this tank, and once the water level rises above a certain amount, the gate will open up due to a differential in the hydrostatic pressure uh, acting on the top and bottom of that gate. So what we're going to do is look at an equilibrium analysis of this gate. The loads we're concerned about here is the hydrostatic pressure that we know is going to be varying linearly with depth. So the pressure that we have is going to be going as rho GH, at least the pressure here at the bottom where H is the depth. So the pressure here again is rho GH. If I want to write this as a line load of force per length, then I multiply the pressure times that dimension B into the page. So as we draw the free body diagram of this gate, what we need to do is write down the single force equivalent of that. So if the load looks like this, we know that it's going to have a single force equivalent, which I'll call F1 here. That's going to be acting on it on that gate due to the hydrostatic load. There's also a reaction force here for C. If I make X to the right and Y up, I've got this. And then there's this contact force down at the seal down here at the bottom. We'll call that N sub A. And we know that this, because it's a triangular load, this distance here, the moment arm about A is going to be H over 3. So as I look at the free body diagram, I guess first I need to write down F1. F1 again is the resultant of that triangular line load. So the resultant is 1/2 the base, which is rho G H times B again being the depth into the page, times the height, which is H. So F1 is equal to 1/2 rho G H squared B. Now I'm going to write down a moment equation about the hinge point there of C. I've got the contact force there at A on the bottom. That's going to have a moment arm of D. And then I will have the hydrostatic load there, F1. It's going to have a moment arm of D minus, let me make sure I got this right, D minus H over 3. And that will be a negative moment like this. And since those are the only moments that are acting about C, for equilibrium that is a 0. So it says here that the normal force, so the contact force on the bottom that keeps the water from coming out the bottom at that seal, that's simply going to be equal to D minus H over 3 times F1, 1/2 rho G H squared B divided by D. So that's what we're going to have in terms of the reaction force at the seal there at the bottom at A. The question though asks really not for that, but it says what's the water height that's required to open the gate? Well, that equation works fine as long as that gate remains closed in equilibrium. So the the point where we have impending rotation of that gate, that's going to occur whenever D is equal to H over 3. So for D equal to H over 3, in other words, H equal to 3D, the gate is in a state of impending rotation. So therefore, if H is higher than D, the gate will actually open. So in this case here, the question here asks for the water depth there, H required to open the gate. So H minimum is equal to 3D in order to open the gate. How did we get here? Well, if we summarize what we did, the key part there was to recognize the pressure load that's acting on that plate. And that pressure load is simply due to the hydrostatic load there on the right side. The line load, the force per length, it's a linear function of the depth. We got that. Its resultant force is F1. And since it's a triangular load, it's that resultant is that H over 3 from the bottom. Hence, whenever I write down my moment equation about C, the moment about C is given by this distance here. So that's going to be this distance D minus H over 3. From that, I solve for the normal contact force there at A. I set NA equal to a 0 to find the minimum H, and it ends up being is that if that water depth is 3 times the distance from the hinge point down to A, then the gate will open.